Every bomb ever detonated in the history of human warfare has been, at its core, a physics experiment. And the physicist who designed it knew exactly what was going to happen before it happened, not approximately, not roughly, but precisely, to within margins that would make an engineer blush. That is the thing nobody wants to sit with. War is not chaos pretending to be orderly. War is order, beautiful, devastating, mathematical order that we have collectively decided to pretend is something messier than it is. Because if we admitted how clean the physics is, we would have to admit something terrifying about ourselves. Let me start somewhere that feels safe, and then I promise I am going to make it unsafe. You think of war as destruction, explosions, rubble, chaos. The word itself conjures something anti-scientific, something raw and animal that operates beneath the level where equations live. And that intuition makes complete sense because when you look at the footage, when you see the photographs, when you read the accounts of people who were there, what comes through is irreducible human horror. Your brain is not wrong to resist the language of physics in that context. But here is what I want to show you today. The physics was there first. The physics was there when nobody had fired a single shot. The physics was there in the drawing board and the calculation pad and the question a young engineer asks at 3 in the morning when everyone else has gone home. And understanding that, really understanding it, not just accepting it as a bumper sticker, changes the question from what does war do to something far more interesting. What is it that physics tells us about our own nature? And why does the answer make scientists so uncomfortable? I want you to picture something. Picture a completely flat, frictionless surface, the kind we always pretend exists in physics problems, which of course doesn't exist anywhere in the real world. But humor me, on this surface you have a ball. You push the ball and it rolls. Now here is the question a physicist asks, and it is the same question whether we are talking about billiards or artillery shells or intercontinental missiles. Given the initial conditions where the ball starts, how hard you push it, which direction can I tell you exactly where it will be in 5 seconds, in 5 minutes, in 5 hours? And the answer for a single object moving in a straight line on that idealized surface is yes, absolutely yes. No uncertainty. Newton wrote it down in 1687, and the universe has been obeying it reliably ever since. Now here is where it gets interesting. The moment you add a second ball, the problem does not get twice as hard, it does not get 10 times as hard. The problem becomes, in a very precise technical sense, qualitatively different. And when you add a third ball, something remarkable happens. For almost all starting configurations, the system becomes what mathematicians call chaotic, which does not mean random. I have to be very careful here, because this is a distinction that genuinely matters. Chaotic does not mean random. It means exquisitely sensitive to initial conditions. It means that a difference too small to measure at the start becomes the difference between entirely different outcomes later on. The universe is still following Newton's laws perfectly. Every single interaction is deterministic, lawful, obliging the equations with the same fidelity it always has. And yet the trajectory of the third ball, long enough after the start, becomes practically unpredictable. Now, I want you to hold that image. 3 billiard balls, chaos emerging from perfect determinism, and I want you to scale it up, not to 30 balls, not to 3,000, to the roughly 300 billion stars in the Milky Way, and to the 7 billion human beings on this planet, each made of somewhere around 7 octillion atoms, each atom interacting electromagnetically with every neighboring atom, each of those interactions precisely lawful, precisely mathematical, precisely the kind of thing you could, in principle, write a Hamiltonian for. In principle. Except that in practice, you are now dealing with a system of such staggering complexity that the chaos you saw in 3 billiard balls looks by comparison like a still pond. This is the first honest thing physics tells us about war. The fact that a conflict has causes you can trace does not mean it has a trajectory you could have predicted. And that matters, because so much of how we discuss war is really about arguing over initial conditions. He started it. No, she started it. No, the treaty of such and such started it. And physicists do this too. We argue about initial conditions all the time. But we have learned from watching dynamical systems that initial conditions and eventual outcomes are not connected in a straight line when the system is complex enough. So part of what physics tells us about war is this: be very suspicious of anyone who tells you they know exactly how a conflict will unfold. Not because they are stupid, but because the system itself defeats that kind of certainty. The equations do not lie, but they do humble you if you are paying attention. Now let me go deeper, because the easy story here is war is complicated and chaotic. Good luck. That's not what I want to tell you. I want to tell you something that surprised me when I first really sat with it. And that, I think, is one of the most genuinely strange things about the relationship between science and organized violence. The physics of destruction is extraordinarily well understood. I mean that precisely and without exaggeration. When you model the blast wave from an explosive, you are solving the Rankine-Hugoniot conditions, a set of equations that govern the conservation of mass, momentum, and energy across a shock front. These equations were worked out in the 19th century by two men, William John Macquorn Rankine, a Scottish engineer, and Pierre-Henri Hugoniot, a French artillery officer who died young at 39, having never seen his most important work properly published. Hugoniot handed the manuscript to a friend on his deathbed and asked him to make sure it reached the mathematical community. The friend kept his word. And today, every time an airbag deploys in a car crash, every time a supersonic aircraft flies, every time an engineer calculates the safe standoff distance from a controlled demolition, they are using equations that a dying man asked a friend to protect. That story moves me every time. Not because it is sad, though it is, but because it illustrates something about how science actually works. Knowledge accumulates regardless of the circumstances of the people who produce it. Hugoniot's illness did not stop his equations from being true. His equations did not care that they would be used, decades later, for purposes he never imagined. The mathematics preceded the application by half a century, and that is almost always how it works. The physics comes first. The physics is almost never developed in a weapons lab. It is developed by people trying to understand the world, and then the understanding gets picked up and used for good things, for terrible things, for things that are both at once in proportions nobody can cleanly separate. This brings me to the thing that has genuinely haunted me since I was young, and I am not going to dress it up. I worked on the Manhattan Project. I was 23 years old, and I thought we were racing against Nazi Germany getting the bomb first, and I thought that mattered enormously, and I think I was right about that last part. I was a calculating machine, literally. I ran the computing teams at Los Alamos, and I was very good at what I did, and I found the problems genuinely fascinating, and I did not stop to feel the weight of what we were building until the day they exploded the first one in the desert, and I remember that I cheered. I actually cheered. We all did. And then later, when the bombs fell on Hiroshima and Nagasaki, and I started to understand what those calculations meant in terms of human beings, something happened to me that I have never been entirely able to explain. I am not interested in telling you whether the bombs should or should not have been dropped. That is a moral and historical and strategic question, and I am a physicist, and I am not going to pretend that physics gives you a clean answer to questions like that. But I will tell you what physics does give you. Physics gives you the answer before the question is asked. The bomb was going to work. We knew it was going to work before we built it, because the physics was settled. The only questions were engineering questions: how to assemble it, how to deliver it, how to prevent premature detonation. The science was complete. The moral question arrived after the technical question had already been answered. And I think that is the true structural problem that physics reveals about war. The gap between what we can do and what we should do is not a gap in our knowledge, it is a gap in our slowness. The knowledge outruns the wisdom. It has done this every time, without exception, throughout the entire history of weaponry. The catapult was built before anyone had worked out a theory of justified siege. The repeating rifle existed before any nation had figured out how to account for the body count it would produce. The submarine torpedo was a functioning weapon 2 decades before international law had any language for what to do about unrestricted submarine warfare. And the atomic bomb was a physical reality before human civilization had developed any institution capable of managing it. Now let me go somewhere that might surprise you. Let me talk about entropy. You know the second law of thermodynamics, or at least you have heard of it. Entropy always increases. Disorder always grows. The universe runs from organized to disorganized, always, without exception, as time moves forward. This is the arrow of time itself. The reason why your coffee cools but does not spontaneously get hotter. The reason why eggs break but do not unbreak. The reason why the universe is moving inexorably from a low entropy beginning to a high entropy end. And there is a tempting analogy here between entropy and war. Destruction increases disorder. Disorder is entropy. Therefore, war is just the second law of thermodynamics playing out in human affairs. I have heard physicists make this argument at cocktail parties, and I always want to push back on it, because it is seductive and it is wrong. Here is why it is wrong. Life is a local decrease in entropy. Your body takes disordered molecules from food and assembles them into exquisitely ordered structures, proteins, cell membranes, neural patterns. It does this at the cost of increasing entropy elsewhere. You exhale carbon dioxide, you radiate heat, but locally in your body, entropy goes down while you are alive. Civilization does the same thing. Cities are profoundly low entropy structures, concentrated, organized, purposeful. A library is a spectacular local defeat of the second law. And war does not merely increase entropy. In the thermodynamic sense, war destroys the local order that life and civilization have spent enormous energy creating. When a city is bombed, you are not just watching entropy increase. You are watching the reversal of centuries of entropy reduction. The second law does not cause war. But war has a thermodynamic signature that is, when you look at it clearly, a kind of energetic statement about what we have chosen to spend our negentropy on. Let me give you a thought experiment that I think makes this very concrete. Imagine that you are standing outside in a field, and you are holding in one hand a loaf of bread, and in the other hand a hand grenade. Both objects represent stored energy. The bread represents chemical energy, the organized molecular structure of carbohydrates, fats, proteins, roughly 250,000 calories per kilogram in terms of metabolic energy. The grenade represents chemical energy too in the explosive material, in the metal shrapnel, in the spring mechanism, roughly comparable in mass to the bread, considerably lower in caloric content, but with a radically different time profile for energy release. The bread releases its energy slowly, over hours, through the elaborate biochemical process of digestion and metabolism. The grenade releases its energy in microseconds, a flash of pressure, heat, and fragmentation that covers a radius of several meters. Same physics, same conservation of energy, entirely different applications, and here is what I want you to notice. The difference between those two objects is not in the energy. It is in the rate of energy release and the shape of the energy envelope. All weaponry is essentially this taking energy that could be released slowly and usefully and engineering it to release explosively and destructively. War is, at a fundamental level, a choice about the time derivative of energy release. And that is a physics statement. That is as real as anything in this universe. Now I want to talk about something that does not get talked about enough in this context, which is the physics of information. Claude Shannon, one of the genuinely great minds of the 20th century, a man who worked at Bell Labs and spent his spare time juggling while riding a unicycle down the hallways, which tells you something about how the best physicists think Claude Shannon proved in 1948 that information has a precise physical meaning. He showed that information can be quantified, that it obeys mathematical laws, and that there is a fundamental limit to how efficiently it can be transmitted through a noisy channel. His work is the foundation of every digital communication system on Earth. But Shannon's insight also applies to something that turns out to be crucial in understanding warfare: the role of uncertainty in conflict. One of the most important concepts in military strategy, one that generals have understood in practice for thousands of years, long before anyone had the mathematics to describe it, is the concept of the fog of war. You do not know where the enemy is. The enemy does not know where you are. Both sides are operating on incomplete information, and both sides are trying to reduce their own uncertainty while increasing the enemy's uncertainty. This is, in Shannon's terms, an information theoretic problem. And what physics tells us is that there are fundamental limits to how much you can reduce uncertainty, especially when the system is dynamical, when it is changing while you are trying to measure it. The Heisenberg uncertainty principle is the most famous version of this at the quantum level. But the classical version, the version that applies to armies in the field, to satellite reconnaissance, to electronic warfare, is just as real, and it has the same character. There is always a residual uncertainty. There is always something you do not know. And conflicts that assume complete information will fail in ways that were completely predictable from the start. This is historically demonstrable. The German plan in the First World War, the Schlieffen Plan, assumed with great confidence that France could be knocked out in 6 weeks, at which point Germany would pivot east and deal with Russia. The plan was geometrically elegant. It was a piece of classical mechanics applied to armies' known positions, known velocities, known objectives, calculated outcome. It failed within the first month because the information was wrong, because the terrain was not the assumed terrain, because the resistance was not the assumed resistance, because human beings in mortal danger do not behave like billiard balls on a frictionless surface. The plan was brilliant, and the plan was wrong, and the wrongness came from ignoring the irreducible noise in the channel. Shannon would have predicted this. He would have said, "You have modeled a noisy system as if it were noiseless." Of course the signal degraded. There is a deeper question here that I find genuinely unresolved, and I want to be honest about that, because honesty about uncertainty is one of the things that makes science different from ideology. The question is this: is there a physics of decision-making? Not just a psychology, not just a neuroscience, but an actual fundamental physics of the process by which human beings individually and collectively choose to go to war or choose not to. We have some pieces of this. There is work in statistical physics that models social systems as many-body problems where individual interactions aggregate into large-scale phase transitions, sudden shifts in collective behavior that look very much like the phase transitions in physical systems, like water suddenly becoming ice. A society that is stable for decades can cross a threshold and become violently unstable very quickly, not because the individual components change dramatically, but because the interactions between them reached a critical point. This is a real mathematical framework. It is not a metaphor, and it suggests something important, that war is not always the result of extraordinary causes. Sometimes it is the result of ordinary causes crossing a threshold. The individual atoms of water do not behave differently right before freezing than they did right before, but the system does. Where the physics breaks down, and I want to be very clear that it does break down, is at the level of intentionality. Physical systems do not intend anything. Water does not decide to freeze. A bomb does not decide to explode. But human beings make choices, and those choices are influenced by values, by culture, by love, by hatred, by fear, by hope, by things that do not appear in any equation I know of. Now, maybe they eventually will. Maybe a complete theory of consciousness will turn out to be derivable from quantum mechanics and neuroscience and information theory in some combination that nobody has yet worked out. I genuinely do not know, and I want to say that clearly. This is an open question. The relationship between physical law and human intention is one of the deepest open questions in science, and anybody who tells you it is settled in either direction is telling you something that is not supported by the evidence. What I can tell you is this: the physics sets the constraints. It tells you what is possible and what is not. It tells you how much energy is available, how fast information can travel, what the fundamental limits on accuracy are, what the thermodynamic cost of complex organization is. These are not small constraints. In a very real sense, every war in history has been fought inside a physics problem, bounded by these constraints. And any strategy that violated them, any strategy that assumed unlimited energy, perfect information, lossless communication, frictionless movement, failed. Not eventually, immediately. Physics does not wait. Let me tell you about a moment in the history of physics that I think is extraordinarily relevant here, and that almost nobody outside the physics community knows about. In 1914, a young German physicist named Fritz Haber won, or rather was about to win, the Nobel Prize for discovering a process that could take nitrogen from the atmosphere and convert it into ammonia, which could be used to make fertilizer. The Haber-Bosch process, as it came to be called, is arguably the single most important technological development in human history. Half of the nitrogen atoms in your body right now came through that process, or a derivative of it. Without it, the Earth could not support more than about 4 billion people. We would not all be here. Haber saved billions of lives. Fritz Haber also personally supervised the first large-scale use of chlorine gas as a weapon in warfare at the Second Battle of Ypres in 1915. He was present at the release. He went back to Berlin afterward and was feted as a hero of the German war effort. His wife Clara, also a brilliant chemist, one of the first women to receive a doctorate in chemistry in Germany, confronted him about it, called it a perversion of science, and shot herself with his service revolver 10 days after the attack. Haber left for the Eastern Front the next morning. I tell you this story not to render a verdict on Fritz Haber. History has rendered many verdicts on him, and they are all complicated, and none of them is entirely satisfying. But because it is the most concentrated example I know of the fundamental duality that physics presents to us. The same understanding of chemical bonding that allows you to feed billions also allows you to kill thousands with a cloud of gas. The same knowledge of nuclear physics that powers a city can destroy one. The same understanding of aerodynamics that allows you to fly across the ocean allows you to deliver a bomb with precision. This is not a coincidence. This is not a failure of scientific ethics. It is a structural feature of knowledge itself. Physics does not come with a label saying approved uses only. It comes as truth, clean, neutral, available, and we decide what to do with it. Now I want to zoom out very far. I want to go all the way out to the deepest question because I think this topic earns that journey. One of the most astonishing facts about the universe is that it is describable by mathematics at all. This is something that physicists have noticed and remarked upon with varying degrees of wonder for centuries, but Eugene Wigner put it best in 1,960 inches, an essay called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. Wigner pointed out that mathematics is developed by people following aesthetic and logical principles with no particular reference to the physical world. And yet repeatedly, in case after case, the mathematics turns out to describe physical reality with a precision that goes far beyond what anyone had any right to expect. The equations of general relativity were developed before we had the observational tools to confirm them. The mathematical formalism of quantum mechanics predicted phenomena, electron spin, the existence of antimatter, the Lamb shift that nobody was looking for. The mathematics was always ahead. Always. Why? Nobody knows. This is genuinely one of the deepest unsolved problems in the philosophy of science, and it is not a question about details or data. It is a question about the nature of reality itself. Is mathematics discovered or invented? Does the universe run on mathematics the way a computer runs on code? Or do we just happen to find mathematical structure useful for describing patterns that are, in some deeper sense, not mathematical at all? I bring this up in the context of war because I think it points to something important. If the universe is, at its most fundamental level, mathematical, if the laws of physics are not merely descriptions but prescriptions, not just models, but the actual structure of reality, then what does it mean that those laws do not distinguish, even slightly, between constructive and destructive applications? The equation that describes the explosion does not contain a variable for human suffering. The Rankine-Hugoniot conditions are perfectly indifferent to whether the shock wave is propagating through rock in a mine or through flesh in a battlefield. The mathematics is the same. And that neutrality, that absolute total neutrality of physical law, is either the most important fact about science and warfare or the most disturbing one, depending on which way you turn it. Here is the way I turn it. If the laws of physics contain no moral content, and they do not, I am very confident about this, then the moral content has to come from somewhere else. It has to come from us. It has to come from the species that alone, among all the things we know of in the universe, can look at the Rankine-Hugoniot conditions and ask, should we be applying these here? The capacity for that question is not in the physics. It cannot be derived from the physics. But it exists, and it is real, and it is as far as I can tell, one of the most remarkable things about the universe that it produced, through the blind application of its own lawful processes, entities capable of asking whether those processes should be applied in a given direction. The paradox of the physicist and war is exactly this. We are the people who understand more clearly than anyone how the destructive mechanisms work. We can calculate the yield, predict the blast radius, model the fallout pattern, and precisely because we can do those things, precisely because the calculations are correct, we are the people who should be most invested in the question of whether they should be done. Not because we are more moral than engineers or poets or politicians, but because the precision of our knowledge about consequences makes the moral question harder to ignore. When you know exactly what you are doing, the question of whether you should do it presses on you differently than it does when you are guessing. There is a famous story about Oppenheimer, Robert Oppenheimer, the scientific director of the Manhattan Project in the days after the Trinity test, the first nuclear detonation. He quoted the Bhagavad Gita, "Now I am become death, the destroyer of worlds." That line has been quoted so many times that it has lost its shock. But think about what it means for a physicist to say it. Here is a man who spent years calculating, modeling, predicting, who turned the deepest knowledge of matter and energy toward a single engineering goal, and when the goal was achieved, he reached not for another equation, but for a Sanskrit poem 3,000 years old, because the equations had answered their question, and a completely different question had arrived. Physics can tell you how to build the bomb. Physics cannot tell you whether you should. Physics can model the blast wave. Physics cannot measure the grief. Physics can calculate the optimal conditions for maximum destruction. Physics cannot, and I want to say this very carefully, physics cannot prevent itself from being used. It is knowledge. Knowledge is inherently transmissible and inherently neutral and inherently powerful. The moment it exists, it is available. The question of what it is used for is a question that belongs to the beings who possess it. I think about that every time I work on a physics problem. Not with guilt. Guilt is not useful, and I am not interested in performing guilt for an audience, but with awareness, with the specific, concrete awareness that what I am doing is increasing the precision with which someone could, if they chose, do something with this knowledge, and that the chain from fundamental discovery to applied catastrophe has historically been much shorter than anybody expected and much more difficult to interrupt once set in motion. Let me come back to the image of the 3 billiard balls, because I want to end there. You have 3 billiard balls, perfect spheres, a frictionless table. You know the position and velocity of each one to the best precision your instruments allow. You start them moving. For the first few seconds, your prediction is perfect. But because of the irreducible quantum uncertainty in the initial measurement, not because you were careless, but because the universe does not allow perfect measurement after about 50 or 60 collisions, your ability to predict where any of the balls are is completely gone. The system has gone chaotic. And this is a mathematical certainty, not a failure of technique. It is a fact about the structure of reality. War is a system with billions of such balls, each one a human being carrying in them the whole irreducible complexity of a life, memories, loves, fears, values, histories, hopes. The physics of such a system is not merely chaotic. It is so far beyond practical prediction that the word chaos seems understated. And yet we enter these systems with predictions. We enter them with certainties. We enter them with the confidence of people who have run the calculation and gotten an answer, forgetting that we are trying to apply billiard ball mechanics to a system where the number of balls is in the billions and none of them are spherical and the table has no edges and friction is everywhere and the initial conditions are measured with the bluntest instruments imaginable. The physics does not tell us not to go to war. I want to be honest. The physics is not a pacifist document. The physics is not any kind of document. But the physics does tell us something that I believe is more useful than any prescription. It tells us how badly we tend to misunderstand the systems we are deciding to set in motion. It tells us that our models are wrong in ways we cannot fully see from the inside. It tells us that the gap between what we calculate and what will actually happen grows faster than we intuit. It tells us that the energy we release in all its forms, from the literal explosion to the informational cascade to the social phase transition, cannot be uncreated once released. The universe is very, very good at increasing entropy. We have never in all of human history managed to put the shattered glass back together. Not even once. The physics has always had the last word on that one. We generate the disorder and the second law keeps it. What I keep wondering, and this is the question I cannot stop turning over, the one that sits with me at 3 in the morning, is whether the same species that is precise enough to calculate a nuclear yield to 4 significant figures is wise enough to sit with the knowledge of what that precision enables and choose deliberately not to use it. Not because the physics demands it, the physics demands nothing, but because we can ask the question, because we are, as far as we know, the only things in the entire 14 billion year history of this universe that can look at a calculation and ask whether it should be done. That capacity, that specific, strange, unreasonable capacity for moral reasoning that exists nowhere in the equations, but produces the beings who write the equations, is either the most hopeful thing about our species, or it is the cruelest joke the universe has ever told. I honestly do not know which.